Hello and welcome back to Calculus 2 section 10.3 on series. So the rest of the chapter is going to be chapter on series. I already distributed the chart of series. We are going to learn 10 tests which would tell us whether the series is convergent or divergent. Now, before we get to those tests, let's first write down what the series is, right? So definition. Series is a sum of the sequence. That's it. Done. Series is the sum of the sequence. Sequence is ordered list of numbers. And now instead of commas, you will put plus everywhere. And you will have the sequence. So now, the series. So an example of the series would be 1 plus 2 plus 3 plus 4 plus 5. And all of these add to 15. This is series because you added a sequence. And over here is the sum of the series. What do I know about this series? It's finite. Finite series because it has only 5 numbers. So if you know all of the values of your series and they actually end in the list, we call that finite series. Now, we are not going to list these. We would like to have a compact way to write this, which is where summation notation kicks in. So notation for the series will be summation of an, where n goes from some number, let's say 0 to some value m for finite series, and summation n goes, let's say, from 0 to infinity for an for infinite series. We don't care about finite series. Why? Why don't we care about finite series? Boring, exactly. They're boring. You know all of the terms. If you have 10,000 terms, just ask a computer to add it in a loop, okay? It's 2 lines of code, 3 lines of code, right? You want to print the answer. So if you have 10,000 terms in a sequence and you need to add them up, you'll ask a computer. If you have 5 of them like I had up there, I'll just add them, okay? So finite series always converge. We can always add the numbers either using our brain or the computer. So we do not care about finite series. I'm just going to say over here in parentheses, well, we can say boring. Boring. Always converge. Done deal. It's the infinite series that we care about because infinite series could add to a finite number and we'll call that convergent, or the infinite series could add to infinity and we'll call that divergent. So we only care about infinite series. And those will break into infinite series. An, you can just put infinity on top, is equal to some number s, which will say converges, or infinite series an, some infinity equals to some type of infinity for divergent. So we care about infinite series, and these 10 tests. Now, if you go back to the sheet I gave you, please look that in the column called series, they all have infinities on top. They are all infinite series, all of them. So now, our job is to learn what is going on. Now, before we actually learn these tests, and you know what these tests are, guys? These tests are actually shortcuts. We're going to work out one of these series long way, and then we're going to realize that that's not the way to go, okay? So, as before, right, we mentioned, you can add numbers or you can memorize multiplication tables, right? And you chose to memorize multiplication because you really don't want to add 8, 9 times every time you need it. Also, with the derivatives, you can either use the limit procedure to find the derivative or memorize the shortcuts, which are the formulas. You memorize the shortcuts. Integration, you can crank the Riemann sums, right, with from chapter 5, or you can work out the methods we learned in Calc 1 and Calc 2, including use sub and trig sub and all of that. All of those are actually shortcuts, okay? For series, you can either do the long way, which I'm going to present now, to see if it converges or diverges, or you can learn the shortcuts which are presented in the list of the 10 tests that are provided to you. All right, let's first see what it means, right? What does it mean for a series to converge? So, what does it mean? Convergent series is the series whose limit of partial sums is convergent. Now, this might not mean a lot to you, but let's take a look at a series of, let's say, 3n minus 1, starting at 1, going to infinity. My an is equal to 3n minus 1, and the sequence associated with 3n minus 1 is 2, 5, 8, 11, 14, going on to infinity. Why do I need sequence? Because I am working on the sequence of partial sums. Partial sum 1 is just the first term 2. Partial sum 2 is the sum of first 2 terms, and in this case it's 7. Partial sum 3 is a0 plus a1 plus a2, which is, when I add all of these numbers, 15. Partial sum 4 is a0 plus dot 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 a3, which in our case would be 26. And one more, partial sum 5, a0 plus dot 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 through a4, that's 5 terms, it's going to be 40. If I take now the sequence of partial sums, which is, call it Pn, 2, 7, 15, 26, 40, we see that this is going to grow without a bound. So when I say limit of partial sums as n goes to infinity will end up being infinity, which means that the series 3n minus 1 diverges because its sum never adds up to a finite number. Every time we calculate the next partial sum, it will be larger number, and when you take the limit of all of those, you see that they are going to infinity. They grow without a bound, so the limit of the partial sums, right, is going to be infinite. Now we can take a look at another example. Say you look at the summation of 1 over 2 to the n from 1 to infinity. your an is 1 over 2 to the n. This is a perfect example to pause and really focus on, you have a series on the left and the sequence on the right. Two different worlds. The list of numbers and the sum of that list. So sequence is always the part of the series, right? Anytime I write the summation, you know I'm talking about series. Anytime there is no summation, I'm talking about sequence. Those are the two creatures that we have in chapter 10. That's it. It's nothing else. So I write my list over here when n is equal to 1, because the series told me I should start counting at 1. You can put any number there, 10, but we'll start at 1. So it's 1/2, 1/4, 1/8, 1 over 16, 3 dots. I'm going to bail quickly on this one. What are my partial sums? P1 or P0, whatever you want to call it. P0 is equal to A0 equals to 1/2. P1 is equal to A0 plus A1, which is 1/2 plus 1/4, which is 3/4. And then P2 is equal to A0 plus A1 plus A2, which is 1/2 plus 1/4 plus 1 over 8. So that's going to be, is that 5/8? 7/8. 7/8. 7/8. P3, A0 plus A1 plus A2 plus A3 is going to be 7/8 plus 16, so that's going to be 14 plus 1, 15, right? Over 16. 15 over 16. And we can you guess the next one? I don't have the numbers. Can you guess it? If you look at the pattern?
31 over 32.
31 over 32. Very good. Do you see how numerator goes up by 1 and denominator goes up by 1? Awesome. So now, if we want to check for convergence of divergence of the series, I would have to check for the limit of Pn as n goes to infinity, which means that now I have to figure out the formula to take the limit, right? Because these numbers are not clearly increasing like the ones we had before. So what is my formula? I need to figure out what to do with 1, 3, 7, 15, 31, starting at 0, divided by 2, 4, 8, 16, 32. Those are easy. Yes. What do you got?
It's 2n minus 1 over 2n. 2 to the power of n. 2 power. 2 to the n minus 1.
Plus 1. N plus 1, right? Because our first is 0. We started at P0 up there.
Oh, then take the negative 1 off the top. Then.
And put a plus 1 or no?
Wait. I'm sorry.
No, it's not odd numbers. I don't have a 5. I don't have a 9 and 11 and 13. So,
Wait, we're starting from 0, right?
They already said it. 2 to the n minus 1.
Doesn't make sense because then if n is 0, then it's going to be 0.
Yeah.
Then it's 0. So it's going to be 2n to 2 to
the n plus 1.
Yeah.
2 to the n plus 1 minus 1. Okay. Fixed it. Oh, you want to start counting at 1? Well, I started at P0 over here. It doesn't really matter. We just need to see if this is going to converge or diverge. That's all it is. So now I have to do a limit. N goes to infinity of 2 to the n plus 1 minus 1 divided by 2 to the n plus 1. Awesome. So this is going to be now given as, I don't need this stuff here. So this is just 2 to the n plus 1. Okay, good. All right, so this is now limit. N goes to infinity. When you have addition and subtraction upstairs, you can split, right? So that splits into 2n plus 1 over 2n plus 1, and then a separate problem of 1 over 2n plus 1, because it's a common denominator, right? Now these puppies cancel down to 1, right? Awesome. And this one goes to 0 because you are dividing 1 by infinity. Converges. Right? Oh, we just added infinitely many numbers. Awesome. Computers can't do this, by the way. Yet. When computers can do this, we're done as a species. All right? We are done. Cool. That's not a fun process. Right? Because you had to come up, you had to isolate the sequence, you had to write out the sequence, then you had to go through the addition of these numbers, then you had to come up with a formula for that sequence of partial sums, and then you had to do the limit of that sequence. It's just way too much stuff. So how about we come up with a method that you just look at the problem and just write the solution and you move on. Cool, right? This is where we start learning our methods from the sheet. And the first one, which will actually address this particular problem, is going to be geometric series. Geometric series, the test states the following thing. If you have the form of geometric series start at 0, go to infinity of a r to the n, so if you have this form, a r to the n, it breaks into two possibilities. R between -1 and 1, we have convergence, and R outside of 1 or 1, divergence. If series converges, sum is given by S equals A over 1 minus R. That's in your comments on the sheet. Put the cloud. Start tattooing this as your first tattoo if you want to cheat on the test. Now, I am going to redo the problem we just did, summation 1 to infinity of 1 over 2 to the n. I am going to rewrite this as a summation of 1/2 to the n because I can. I'm going to say that r is equal to 1/2, which is less than 1, it converges, and walk away. Welcome to series. If you don't have this memorized, you don't get to solve the problem. This is what it took, algebraic manipulation, to to put the n up there and say r is 1/2, and I memorize that r between these two numbers is convergence, I'm done. No calculations, no integrals, no derivatives, nothing. Just look at the problem. And you write convergence, you're done. Yes?
Shouldn't the number under the sum be 0?
That's important for the second part. If we want to know exact sum, we'll have to fix that, and we'll have to do something that's called shifting the counter, which we are going to do after 2 examples from now. But excellent eyes, yes. That's extremely important. You cannot find the sum. You cannot use this formula here until you make this into a 0, and there is a procedure that you have to use. I don't want to teach it now. I just want to do another 2 examples, and then the next one will be the one where we're going to work with that. Here's the next example. Summation of 4 to the n from 0 to infinity. The question for the entire chapter 10, converge or diverge? What is it? Would you bet your money on it? You would? Okay, how much? Right? Because yes, I'm not joking, guys. This is how easy this is if you know the bubble. R is 4, bigger than 1, diverge, move to the next problem. That's all it is. Learn the bubble. All right, spicy one. Summation 0 to infinity for 2 to the n plus 3 to the n divided by 5 to the n. This was on NGIT Calculus 2 exam when I used to teach there. This particular problem. What do we know about fractions? What do we know about fractions? What can we do? We can split them. And then each one will get its own sum, because summation is just addition. So you can just split. So, a little bit of algebra witchcraft here. This is going to be summation of 2 to the n divided by common denominator plus, if this is a minus, it will be a minus, 3 to the n over 5 to the n. Come on, pen. You have these infinities and zeros and all that good stuff. Now, more algebra. We stuff these into single exponents, right? And now what do we know? Each one converges. So each one of these, this one is less than 1, this one is less than 1. So done deal. Yay! Find the sum. Summation 0 to infinity of 3 times 1/4 to the n. There's no equal sign there. What should I do? Use the equation. Very good. S equals A over 1 minus R. A is 3. 1 minus R is 1 over 4. Excellent. Multiply by 4 everywhere to kill the double fraction. 12 divided by 4 minus 1, which is 12 divided by 3, which is 4. This series adds to 4. Infinitely many numbers that we get to add between 0 and infinity, add to 4. Awesome. Find the sum. Summation of, let's go 2 this time, of 3/2 to the n, 0 to infinity. Yes, sum is what the series converges to, exactly. Yep. Yes? Nice. I tried. Equals infinity. It's a divergent series. It's 3/2 is bigger than 1. So, right? Cool. Ready? Summation 2 to infinity of 3 times 1/2 to the n. All right. Now, guys, for this problem, we don't have 0. We see it 1/2, so it converges, so we can find sum. And because we don't have a 0 under the series, we have to do something that it's called shifting the counter. So here in blood, not 0, we must shift the counter. Those of you going to differential equations next semester or the following or whatever, you must know this, because you will be shifting counters on power series to solve differential equations. So this is shifting on series. It works the same everywhere. So you must know this procedure. Very important. How do we shift the counter? Well, first, I know that R is 1/2. I'm going to keep that. And here is what I'm going to write, and you will understand it later. A is not 3. You say, hold on, you said so. No. You'll see A is not 3. In this problem. Why is it not 3? Because that's not 0, it's a 2. And you'll see that that 3 will change. I know what it is, but I don't want to spoil it. So, how do we shift the counter? We have n going from 2 to infinity of 3 1/2 to the n. I need to bring this to a 0. I will get that if I subtract 2. You have to subtract whatever the number is to bring it to 0. So if you start at 1, subtract 1. If you start at 7, subtract 7. So what you have now is the new n minus 2 is equal to 0. Now, it's not really nice to have a counter that it's n minus 2. So how about you define that to be k? So now it's k equals 0. You see what we did? What is this? This is like u sub, right? We needed to shift that to 0, and that produced n minus 2, and now I'm just going to call that n minus 2k. Awesome. So now I know that k is n minus 2, from where n is k plus 2. So what is my series now? My series is k is 0 to infinity, 3 1/2 to the, I'm not allowed to put n. I just changed my counter to k. So what do I have to put up there instead of n? K plus 2. Yes. At this point in life, you go, ha, we got it. K equals 0. Uh-oh. But it's k plus 2. Now you get to peel off 2/2 to bring it back to k. Because as we fixed this one, we messed up that one. But we can fix this one by peeling off 2/2, right? To bring it back to k. algebra for that is x to the m times x to the n is x to the m plus n, right? So I need to peel off the plus 2, so that's a half squared. So using this algebra now, I have summation infinity k equals 0, 3, here is my 1/2 squared peeled, and here is my 1/2 to the k that has to stay, giving me the new problem. K goes 0 to infinity, 3/4, there's your a, 1/2 to the k. This is the form that matches the definition. Definition had a 0 and n. 0 and k. Awesome, right? So now we know that r is 1/2 and a is 3/4. Remember how I told you a is not 3? A is not 3 because your counter is not 0. Right? So welcome to shifting the counter. So now s is equal to 3/4 divided by 1 minus 1/2. That's 3/4 divided by 1/2. These guys cancel, and you have your 3/2. So sum is 3/2. I don't think I have I don't have them here. The old notebooks for DiffyQ to show you this in the problem, right, in chapter 3. So those of you going to differential equations, this is coming back. You need to know this to shift the counter so they match where they begin. So they all have to begin at the same number. In this case, has to begin at 0. We're done. That's geometric series. You have to use your eyes to look at R and decide just by what R is whether it converges or diverges. That's it. And then you have to be careful with the counter. If it starts at 0, you can go on and compute the sum. And now it's in your hands. You're going to memorize the theorem or not, right? That's it. The second part of the lecture now is going to be telescoping series, which is line number 3 on the chart I gave you. Now, telescoping series do not have a theorem, they have a procedure. And the procedure is to split the series into finite series plus what we call the tail end. And then take the limit and goes to infinity. This is a very crude procedure. We need to do examples for you to understand this. The form of telescoping series, you can start it anywhere. Telescoping series can start at 0, can start at any number. Shifting of the counter is the thing only for geometric. All others can start at whatever they want to start, unless there is an issue with the divided by 0 or something that prevents it from. You can start it anywhere. So let's start at, let's say, 1 to infinity. and let's say you have 1 over n minus 1 over n plus 2. Please look at the sheet that I gave you and notice that you have a sequence minus sequence on the line 3. Do we all see that? The bn minus bn plus 1? Could be bn plus 2, bn plus 3, whatever. So we all see that the form is 2 sequences subtracted. That's how you know it's a telescoping series. All right, so now what is this going to be? Well, this is going to be a finite series from 1 to n, m, a different number. You can use m, you can use k, whatever. So that's a finite, plus a term that goes m to infinity, which is the tail end. Now let's see, what am I going to do here? I'm going to start plugging in these numbers from 1 to m. How do I do that? Well, I just replace. The first term is 1 over 1 minus 1 over 1 plus 2. So this is when my n is equal to 1. Plus, because it's a sum, next term is n is 2. So for this first one, n is 1. For the second one, n is 2. For the third one, n is 3. We'll go much more than that, obviously. So now I have, for n is equal to 2, is going to be 1/2 minus 1 over 2 plus 2. Plus, you can imagine it. Plug in 3. What do you mean no? You have to plug in 3 now. For the third term, 3 plus 2, plus, what's the next? 1 over 4 minus 1 over 4 plus 2, plus 1 over 5 minus 1 over 5. We are going to go all the way to m, guys. Plus 2. Now you might ask, well, when is that m? Well, let's do one more. 6 minus 1 over 6 plus 2, plus, oops, it's not supposed to be equal here, it's supposed to be plus. Didn't hit the shift quick enough. Plus 3 dots, and we'll deal with the tail end later. So now I have n is 4, no coughing, and 5, and n 6. Okay. What's happening at the tail end? At the tail end, I'm going to set up a whole bunch of these to match what I have up there. And I'm going to start working out this backwards. The last term would be the same as the original problem, just with m's or k's or whatever. Because remember, my last term in a finite series is going to be when I plug in the last number, which is m, into original problem. The term before, so this is my n equals m. And this one is n equals m minus 1, which is the term before. So that's 1 over m minus 1 plus 1 over m minus 1 plus 2. Oh, these are minuses in between, yeah. Minus and a minus, yes, thank you. So the next term over here is n is equal to m minus 2. So we have 1 over m minus 2 minus 1 over m minus 2 plus 2. The next term, going back again, is n is equal to m minus 3. That's going to be 1 over m minus 3 minus 1 over m minus 3 plus 2. You're going to say, is this really necessary? Yes. Next term is m minus 4, 1 over m minus 4, minus 1 over m minus 4 minus plus 2, plus 2. And the last term we're going to write here, n equals m minus 5, 1 over m minus 5, minus 1 over m minus 5 plus 2. Got it. We'll just simplify everything. What do I have on top? 1 minus 1/3 plus, next, 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6 plus, what's next? 1/5 minus 1 over 7 plus 1 over 6 minus 1 over 8 plus plus, simplify these, 1 over m minus 5 minus 1 over m minus 3 plus 1 over m minus 4 minus 1 over m minus 2 plus 1 over m minus 3 minus 1 over m minus 1. If you get the bingo, just yell it out. 1 minus m minus 2 minus 1 over m plus 1 over m minus 1 minus 1 over m plus 1 plus, and the last term over here, for simplifying, 1 over m minus 1 over m plus 2. That's simplified. Does anyone see what happens now? Something will go to 0 eventually, yes. But what happens before something goes to 0? Do we all see negative 1/3 and a positive 1/3 to cancel? Go on, kill them all. What do we have? Negative quarter, positive quarter. Negative fifth, positive fifth. Negative sixth, positive sixth. You see how they all cancel? The first two survived over there, 1.5. Everything else cancels. So there will be a negative 1 over 7 to cancel here and a negative 1 over 8 to cancel in there. Go backwards now. Do we have 1 over m to kill it? Of course we do. Do we have 1 over m minus 1? Yes, we do. M minus 3? There it is. M minus 2? Got it. M minus 4 will die right there. M minus 5 will die right there. What is left? What's left is 1 plus 1/2 plus the limit of negative 1 over m plus 1 minus 1 over m plus 2. Well, that puppy goes to 0. And your sum converges at 3/2. I beg you, when someone asks what's new, please, please bring it up. Hi, honey, how was school? Bring the chair. Pull up the chair. Let's go.
Watch a simple trick to get carpal tunnel.
Oh yeah, these problems are amazing. For killing time and carpal tunnel, this is, you have nothing better on the market. Well, there are a few things that you can also do, but this ranks high up. Welcome to telescoping series. What's next? Well, ln of n minus ln of n plus 1. 1 over square root of n minus 1 over square root of n plus 1. Or n plus 3, or right? And how many parentheses do you have to write? As soon as you reach the first parenthesis, which cancels both terms, you can stop. So I would have to write all the way here, because it's here where 1/5 kills the 1/5 from the first parenthesis that had both of them crossed out, right? So I would have to go 5 terms. I went
full extra term.
Well, for you, that's, because I care, right? So I went 1 extra term to kind of make a point. But the idea here is that you keep writing these, and 5 terms would probably be the minimum. The further away these guys are, more terms you need until they start canceling. How far away these are? 2 away. 1, 2. If they're 3 away, 1, 2, 3 would survive. If they're 4 away, 1, 2, 3, 4 would survive. That means that you would have to write 9 terms in order to cancel the first parenthesis. The further apart they are, the worse the situation. Now, is there any calculus here? Yeah, you took the limit to get a 0 at the end. So sure, there was some calculus. But mainly is, right, just writing this stuff out. It's brutal, right? So let's take a look at what beautiful things they would suggest and a homework so you can enjoy. Oh, beautiful. So they have 1 over k plus 1 minus 1 over k plus 2. Those are 1 apart. Then they have 1 over k plus 2 minus 1 over k plus 3. And they also 1 apart. And they're the same, right? But then the next 4 problems look a little bit different. It says summation of, it starts at 1, goes to infinity, and it says 1 over n plus 6 times n plus 7.
No.
Yes.
No.
You got it.
No.
So what now?
Oh my, partial fraction decomposition.
Yes. Partial fraction decomposition to convert this into a form that will have a minus, then you get to enjoy the problem. I know. But again, those of you going to differential equations will need partial fraction decomposition for inverse Laplace transform. So it's always good to kind of practice partial fraction decomposition. So let's go. I know. It's a over n plus 6 plus b over n plus 7, which is an plus 7a plus bn plus 6b is equal to 1. So n equation is a plus b equals 0. and then we have 7a plus 6b equals 1. That's the constant, right? Now we can say that a is negative b or b is negative a, whatever, and just plug in. That's the fastest way. So we have negative 7b plus 6b equals to 1. That's a negative b equals to 1. b equals negative 1. And if b is equal to negative 1, then a is equal to positive 1. Ah, there's lag. Oh, there you go. Okay, good. So now, this problem is actually summation 1 to infinity of 1 over n plus 6 minus 1 over n plus 7. And all we need to do now is to write all of that stuff out, cancel. Right? There's nothing that, cup of coffee in 30 minutes.
12 pages of paper.
Oh yeah, this is going to be it. Like this one homework, that's a Sunday. Completely ignoring everything else. Or neglecting, whatever. Alright, so n equals 1. That's 1 over 7 minus 1 over 8. Plus n equals 2. 1 over 8 minus 1 over 9. Plus n equals 3. 1 over 9 minus 1 over 10. Plus 1 over 10 minus 1 over 11. Plus, I can stop because I already see the cancellation. The 1 8 kills 1 8 and 1 kills 1 9. So I have the parenthesis that I even went an extra term, right? The 11 will die right there. So when they are 1 away, I mean, it's really quick solution. Plus, set up 3 of these. It's enough. So the last one is always the same as you can use m's, you can use k's, whatever makes you happy. Then, so let me just write. The first term is n is 1, n is 2, n is 3, n is 4. The last term n is m minus 1, n is m minus 2. So when it's m minus 1, so that's going to be 1 over m plus 5 minus 1 over m plus 6, and then 1 over m plus 4 minus 1 over m plus 5. So now the cancellations, we have m plus 6, m plus 6, m plus 5, m plus 5. This one will cancel in there. And what I'm left with is 1 over 7 plus the limit m goes to infinity of negative 1 over m plus 7, which is 1 over 7 plus 0, which is all of this goes to infinity. Yeah. So partial fraction decomposition to the rescue. One more example, and this is to try 1 to infinity square root of k plus 1 minus square root of k. The book likes k, Larson book likes m. You'll find the book that's going to use m. It doesn't matter. 18 seconds left. Okay, let's go. I know, tough times, man. All right, so it's already with the right there with the minus sign, with the negative, so no partial fractions necessary. We'll just plow through substitutions. We are starting at 1, so the first value that we sub is 1. So for n equals 1, n equals 2, no, these are k's. K, there we go. All right, k equals 3, and so on. So what do we have? The first one is square root of 2 minus square root of 1 plus square root of 3 minus square root of 2 plus square root of 4 minus square root of 3 plus, and I'll put dot 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 because I already see that, let's go blue, root 2 dies with root 2, root 3 dies with root 3. I already have a parenthesis that has both of them canceled, which means root 4 would cancel in there. So we don't have to worry about that. And then we have the tail end. So I'll set up the same what I have for the tail end. The tail end, you start from the back. You can say m plus 1 minus root m. So this is k equals m. K equals m minus 1. K equals m minus 2. So to go to the previous term, you are subtracting numbers. To go to the next term, you are adding numbers. So it's the easiest to start from the back because it always looks the same as the problem. So now when you're subtracting 1, it's going to be root m minus 1, root m minus 1 minus root m minus 2, and so on. When you cancel these, root m gone, root m minus 1, root m minus 1 gone. You have the parenthesis that cancels both. So now you'll have that one cancel in there. And you are left with negative 1 plus the limit of square root of m plus 1 minus root, sorry. That's it. Sorry. M goes to infinity. Okay, so right, because this puppy over here is going to be infinity. Awesome. I hope you're not disappointed, but that's it. So tonight we finished the sequences and we finished the introductory lesson of what the series are, what it means for infinite series to converge or diverge. We saw the tough way, let's say, the long way, where you have to find the sequence of partial sums and then figure out the formula and then do all that stuff. And then we saw first 2 out of the 10 tests, geometric and telescoping. Now, the next step for you for this sheet, there's one more thing that you should mark on it. You are going to take a look at the comment section for telescoping and geometric. Look at all other columns. None of them tell you the sum, other than these 2. So we will have 2 tests where we can know what the series converges to, and that's geometric and telescoping. Those are the 2 special tests. The only 2 tests that can tell you what the series adds up to if it converges. You will have convergence for p-series. You will have no clue what it adds up to. Right? You just know it has a finite sum, and you have no clue what it is. For all others that converge, other than the first test is only divergence, right? So you have 7 tests below telescoping series. All of them converge, and you'll have no clue where they converge to. So the only 2 tests where you know the sum is geometric and telescoping, and everything else is you'll have no clue. Okay? So make sure you make that note that geometric and telescoping, we know the sum. We can calculate the sum. We can say series converges to, what do we have earlier? 1/7? Was that what we had? Yeah. So we will say here series converges to 1/7. So you know what it converges to. It converges to 1/7. That means the sum of infinitely many numbers for that series adds to 1/7. So series converges to 1/7. And we have the formula to compute geometric series sum. We do not have any of those for the 7 tests below. So all of those other tests, when they converge to whatever value we don't know. We can't compute. There are numerical methods, there are partial sums. Obviously, the computer science geeks can write quickly the code, right? Look at the first, 10,000, 100,000 terms. It should give you a very good sense of what it converges to. But in terms of the, calculations like these, we don't have anything for those. So that's it. Bye.